present your paper.
Okay. Make it here. Okay. So good morning, everyone. Today I will present a paper on combining self-reported and sensor data to explore the relationship between fuel poverty and health well-being in UK social housing. It's a paper co-authored with Karyn Morrissey, Richard Sharpe, and Tim Taylor. And my name is Gengyang Tu. Actually, I'm a research fellow at the European Center for Environmental Health and Environment and Human Health at the University of Exeter. So first, let me give you some context about the study. Fuel poverty is a growing problem affecting approximately 2.5 million UK households, and the heating during winter is the central problem. In the literature, we have found that socio-economic characteristics, rurality, tenure, and housing characteristics are the determinants of fuel poverty. And fuel poverty has a significant impact on both physical and mental health. In addition, low-income populations are more likely to live in social housing sector and more likely to be fuel poor. In terms of fuel poverty measurement, so far, fuel poverty is commonly measured applying self-report approach, expenditure-based approach. For example, with a common definition, if a household's expenditure on energy pass 10% of their income, in addition, this household have an income that is lower than 60% of the median income of the country. In this case, this household is considered as fuel poor. This is expenditure-based approach. And there is also a temperature-based approach that is rarely used because we don't know the indoor temperature of participant. We can only ask them about this, so it's rarely used. And this one, self-reported approach, is just we ask them, do you feel cold at home? It's a common type of question we ask. So as you see, these approaches are limited due to inconsistent of self-assessment, inaccurate or unknown information on household income and energy expenditures, and also biased self-report indoor temperature. And simultaneously, there is another report suggests that we should apply 18-degree warm standard. And it also suggests that this 18 degrees threshold may be less important for healthy adults. But actually in the UK, we apply this 18 degree. It's an absolute number. And then, so our research objective is first estimate the determinant of fuel poverty and its impact on physical and mental well-being among social housing tenants. It's also because so far there is very few studies focused on social housing tenants. And also, we will combine self-reported fuel poverty with revealed fuel poverty using sensor data. So we will overcome all this problem because we install sensors in participants' homes. So there won't be any bias. So I will present our methodology. First, we use a sensor to measure the real overnight bedroom temperature from 7 p.m. to 7 a.m. And and we cover 3 months, 3 winter months in the UK, which is December, January, and February. And this is the sense you can see it's a white box. There is no information that our participant can see no information. And it's hidden in some place so that, how to say, it cannot influence their life. And it will send our data every 7.5 minutes. And it's very accurate. This is how we measure the revealed fuel poverty. We have 2 measurements. First, we apply a fixed 18-degree criteria. This is defined as E3. So the coldness level equals to 18 degrees minus the temperature of the main bedroom during winter. And if the temperature is already higher or equal to 18, and then the coldness is 0. Of course, the home is not cold. Secondly, we have applied a more flexible criteria, which is denoted as E4. So for participant in vulnerable group, we maintain the same warm standard. That means it's the same. And then for healthy participant, we will test if the 18-degree warm standard is important for them or not. So now we use 17-degree warm standards, and the calculation is the same. And by the way, I have also tested 16-degree and 15-degree. The result doesn't change. That's why I stay with 17-degree. And according to the literature, the vulnerable group includes participants who are more than 65 years old and people with respiratory diseases or with a disability or long-term sickness. This is how I measure the self-reported fuel poverty. So according to recent paper, there is 3 dimensions of fuel poverty. So are they capable to keep their house warm? Second, can they afford to keep their house warm? Third, are they capable to keep their house away from all housing fault? So that's why I had another question. Do you avoid ventilating your home? Because if they just shut all the windows and doors, what will happen in the UK? There will be mold, there will be dampness. So of all the housing fault will come. In the UK, it's very humid. You need to ventilate your home. So this is 3 criteria. I'm just not simply ask them, do you feel cold or not? I use the recent, how to say, criteria developed by other studies. And also, in terms of health well-being measurement, we use a scale a clinical level scale called SF12 Vision 2. So this scale measures 8 health domains, and then it provides a physical health score and a mental health score. This is the framework. So in my empirical analysis, I will apply structural equation modeling. So my fuel poverty, E, depends on the 3 self-reported questions. And I have another hybrid fuel poverty, which depends not only the 3 self-reported questions, but also the coldness of the home. So there is 2 types of fuel poverty measures. One depends only on the self-reported items, and the other one depends not only this, but also the coldness of the home. And then I use social demographic characteristics and housing variables to explain fuel poverty, physical mental health well-being, and the mental health well-being. That's 3 flash. And also I estimate the effect of fuel poverty on physical and mental health well-being. This is the framework. And also in terms of revealed fuel poverty, this fuel poverty E will be directly the coldness level of the home. For the survey was implemented during from November 2017 to March 2018. It's a face-to-face survey with 329 social housing tenants in Cornwall. And among them, there is 280 participants have allowed us to install a sensor in their house. Not everyone agreed to do this. And here is Cornwall. It's the southwest corner of the UK. So it's very easy to find it. And even if our sample is a convenient sample, but we pay attention to the representativeness of our sample. We have compared it with the national average. So we have a bit more, too many female home representative here, and all the other figures are normal. And also in our survey, we have collected information on respondents' socio-economic status, health condition, indoor-outdoor activities, and health well-being scores. And this is the bedroom temperature. So we have found that there is 45.4% of participants live in coldness. That is very impressive. It's UK. And
I think we have a problem. Are you there?
Yes. I think it's only Mr. Gengyang who's disconnected. Let's wait a little bit for him to reconnect. If not, we're gonna see what to do.
Can you hear me now?
Yes, yes, it's working.
Sorry, I was kicked out. I don't know why. And can you see my slides?
Yes, yes, we see it.
Yes.
Okay. So this is the result. First, you can see that older people have less fuel poverty problem. And then if the household size is larger, and then it's less likely that the household is living in fuel poor. And also, household who lives in participant who lives in flats are less likely to live in fuel poor. They got their neighbors, and also you can see that people who spend more times at home during weekend are more likely to live in fuel poor situation. And people who spend more time at home during the week, they are also more likely to report fuel poor. That's a bit different. And for the participant who have COPD, so respiratory diseases, even their house is not significantly colder than the other room, than the other home, but they are more likely to report fuel poor. And here, this is the home energy label of the UK. In our sample, the minimum is D level, and the highest level is B level. You can see that it doesn't really change the fuel poverty situation. So that means even you provide a social housing tenant well isolated home, a home with good insulation, it doesn't really change the situation of fuel poverty. Oops. Here you can see that it's a determinant of mental health well-being. You can see that the stated fuel poverty have a significant negative effect on mental health well-being of the social tenant. And this is the revealed fuel poverty. It also have a very negative effect on mental health well-being. And the last column is the flexible warm standard. You can see that it explains people's mental health well-being better. And this is the determinants of physical health well-being. You can see that the self-reported fuel poverty have no effect on physical health well-being. And it also have, and the revealed fuel poverty confirms the result. Maybe in the UK, even your home is cold, you have another solution like using blanket or wear more clothes, it won't have a impact on your physical health in the short term. Remember that we have only 1 year home temperature data. So in the short term, the effect is mainly on mental health well-being.
Excuse me, you have 1 minute left, please.
Okay, that's a discussion and conclusion.
Perfect.
We find significant determinants of fuel poverty, such as socio-economic characteristic, health conditions, housing conditions, and the individual at-home behaviors. And we have found some difference between the self-reported fuel poverty and the revealed fuel poverty. For example, respondents with diseases such as respiratory diseases report more fuel poverty despite their bedroom is not significantly colder. And also, respondents who live in bigger houses are less likely to report fuel poverty despite the fact that their main bedroom is colder. We find also poor mobility is positively related with fuel poverty. People spend more time at home, report more fuel poverty problem. And also providing an energy efficient house doesn't solve the fuel poverty problem. In general, respondents' preference for indoor warmth is heterogeneous. And to measure fuel poverty, not only the revealed fuel poverty, but also the self-reported fuel poverty should be considered. That's why we should combine them. And at last, a more flexible warm standard is better than actual fixed 18-degree standard. Thank you very much.
Thank you for your presentation. We have time for questions. We have one question from Mahar in the chat. Mahar, do you want to connect your micro to?
Yeah. Yeah, I was just wondering with the actually I had two questions. The one in the chat was simply about the descriptive statistics that you had. And I was wondering, like, when you showed the national average, are you talking about like the UK national average, or are you talking about like social housing tenants in the UK, that average? Then the other one that I was, oh, sorry. Yeah, no, all good.
In fact,
yeah.
A second question, please.
Okay, and then the second question was, I think I might have just missed that, but you were talking about like flexible temperature versus fixed. And I was confused about what you meant there. Like on the last slide, you kind of had like flexible temperature threshold versus a fixed temperature threshold, I think.
Okay, let's start by the first one. Sorry, I was kicked out, and yes, my last part of presentation is not very clear. Sorry for that. So you can see that our source is English Housing Survey, social rented sector. So I'm comparing with the national level statistic, but in the social rented sector.
And does social rented, does that mean like social housing?
Yes.
Or yeah, okay.
And what's the second question? It's yeah, flexible.
Yeah.
Flexible.
Yeah.
So the define of flexible measure is 18 degree for healthy participant. No, it's 17 degree for healthy participant and 18 degree for vulnerable groups. And then you can see the result. Here. So the E3 is the fixed criteria, 18 degree. And the E4 is flexible criteria. You can see that in terms of capacity of explaining the mental health well-being, evidently of the flexible criteria, it's more significant. So the first one is the level of coldness, which equals to 18 minus the indoor temperature. And we got also a square. So I assume that the effect cannot be linear. So you can see that both the main effect and the nonlinear effect, they are significant. So the flexible criteria really explain the mental health well-being better than the fixed one.
Thank you.
Are there any questions? So I have one question. Can you see can you measure the difference of temperature between children bedroom and adult bedroom? You do not have this information on your data?
We have only installed a sensor in their main bedroom, but because we are not sure they have children or not. And also it's very expensive. It costs us 1 million to install sensors in 300 homes. So we haven't installed more sensors. And also I have control. Yes, I have controlled the household size. So if there are children, I will control the effect. I have also tested another variable, which is the number of children, and it's not significant. It's less significant compared to household size. So I decided to use household size.
Okay. And did you see if there are correlation between temperature, bedroom temperature, and other revealed measure of fuel poverty? E1, E2. Yes, E1, E2.
Yes, E1 is the self-reported fuel poverty.
Mm-hmm. And is they correlated with the temperature with bedroom? Is they the same households?
You see, the first column is the result of OLS estimation with bedroom temperature. You can see that most of them are the same, except, for example, this one, household size.
Okay, I'm sorry, I wasn't clear. I was wondering if the household were in fuel poverty according to the self-reporting indicator as the same who live in housing with the cold temperature in the bedroom.
Yes, we can compare it. For example, here, because the E3 and E4 is directly the coldness of of their bedroom. So we can compare the self-reported fuel poverty directly with the result related to bedroom coldness. If the result are more or less the same, that means how to say, we have a more or less the same situation. And if, for example, this one is not the same, and then we need to do some further investigation.
Okay.
But I haven't really, how to say, jointly analyzed these two models. Well, perhaps it's very interesting. But okay. I have this hybrid indicator which combine the self-reported poverty, fuel poverty, and the coldness of the bedroom. Well, it's like a double check.
Okay, thank you. If there is no other question, maybe we can go to the second presentation. We will listen Lisa Becker.
Yes, thank you.
Yeah. So Lisa will present a paper entitled Socio-economic Effects of COVID-19 in a resource-based economy, an analysis using the macroeconomic model E3DZ for Algeria.
Yeah, thank you, Anna. I will
see.
share my screen in just a second. So, yes. So, hello to everyone and greetings from the northern part of Germany. As Anna already said, my name is Lisa Becker. I'm working at the Institute of Economic Structures Research in Germany in the team of climate and energy. And I'm very happy to be here today at the first online conference to present some modeling results and to feel a little bit more connected to the world than in the last month or in the last year. And the following analysis is about the socioeconomic effects of COVID in Algeria as a resource-based economy. So let's have an overview of my presentation. I will start with a short introduction to the model, some background information, and to the scenarios that we have developed. Then I show the assumptions we made for these scenarios, first for the renewable energy development, and second for the economic consequences of COVID. And at the end, we will look at the results and which conclusions we drew from them. So first, we look at the tool we use for our analysis. It's a model E3DZ. It is a national macroeconometric input-output model, which we have developed in a previous project in 2019. E3 stands for economy, energy, and environment. There are the different parts of the model. It is based on macroeconomic as well as sectoral data, and the behavioral parameters are econometrically estimated. The model allows projections up to 2050, although in the following analysis, we have considered only a time horizon up to 2035. To analyze the effects of energy policies or any other policies, the policies need to be translated into economic quantities and model variables, and thus the scenarios can be calculated. And then the deviations between two scenarios can be considered as the result of the respective policy that was set. So, well, initially there was a different presentation planned for last year's conference, which focused more on energy efficiency in the model. But then COVID came, and now we had the opportunity to continue using the model, and thus I can show more current results today. What was the starting point for our analysis? As most countries around the world, Algeria was affected by lockdowns and severe trade and travel restrictions due to COVID. In addition, the international energy markets, which play an important role for Algeria's economy, were strongly influenced by the global recession last spring. And independently of COVID, new targets for the expansion of renewable energies have been passed in February 2020, and their impact is also considered in the following analysis. Well, since COVID, we all know what applies today may be completely different tomorrow. So please keep in mind that the following assumptions were made last summer, and therefore only the developments that were known until then could be included in our analysis. So for our analysis, we developed 5 scenarios shown in this table. They examine the socioeconomic impact of COVID and the expansion targets for renewables. So there's one scenario called S3. It represents a world that would have been possible without COVID and in which the new expansion targets are met. The other 4 scenarios on the right side are a combination of different assumptions for economic development and for the expansion pathways for renewables. So on economic side, they distinguish between a rapid economic recovery of COVID and a slower one. And for the renewable expansion, they distinguish between maintaining the new targets called stated policy scenarios on the one hand, and on the other hand, only achieving lower targets due to COVID, which are called reduced ambition scenarios. So to give an example, scenario 5.1 is a combination of a rapid economic recovery and reduced expansion targets. So to build these scenarios, we need quantitative assumptions for the expansion pathways and for the economic variables. So first of all, the renewable energies. We see here the development pathways. The 2 yellow dots mark the targets for 2024 and for 2035. In scenario S3, it's the dark blue line. Both targets are reached on time with a constant expansion. In scenarios 4.1 and 4.2, the expansion is slowed down by COVID at the beginning. So the first target is only reached with a delay, but then can be caught up until 2035. The expansion for scenarios 5.1 and 5.2 is shown by the green line, and here the deficit caused by COVID at the beginning cannot be made up, so that only 9,000 instead of 15,000 megawatt will be expanded by 2035. So now just a brief overview of the economic assumptions. We have reduced the production volumes of oil and gas in line with the levels that were foreseeable last summer. In addition, the oil and gas price development have been strongly dampened by the negative shocks on the international energy markets. And these reducing effects last longer in each case in the slow recovery scenarios than in the rapid economic recovery scenarios. In addition, we have adjusted variables on macroeconomic level to reflect the developments due to COVID and the changed consumption patterns, in particular that were private and government consumption and investments. Yes, and if you're interested in the specific assumptions about the economic consequences, there's a more detailed overview in the backup slides. So let's get to the results. First of all, scenario S3. Here we see the projected development that could have resulted in a world without COVID. The figure shows the annual growth rates of GDP in light blue and employment in dark blue. The growth rates are consistently positive. For GDP, they are between 2.6 and 1.7%, and for employment between 2.4 and 3.0%. So now we look at the S4 scenarios. That means 4.1 in light blue and 4.2 in dark blue. In both scenarios, GDP drops sharply by 6.7% in 2020. And this effect is mainly driven by the change in foreign trade, in particular by lower exports of oil and gas, which are less demanded on the international market and for which prices have fallen sharply due to COVID. in scenario 4.1. The rapid economic recovery means that GDP can grow by 6.2% in 2021. And this is due to the recovering prices of oil and gas and to production volumes which rise again. And in addition, there will be more consumption and investment again. And if the economy recovers more slowly, as in scenario 4.2, GDP will only grow by 2.3% in 2021 due to the continuing restrictions imposed by COVID. So now we want to compare these results we've got from the S4 scenarios with the scenarios 5.1 and 5.2, in which the expansion targets for renewables are not met. So again, as a reminder, because I think it's a bit confusing, 5.1 assumes a rapid economic recovery as in 4.1, and 5.2 assumes a slow economic recovery as in 4.2. So the second number indicates the speed of recovery. So by comparing, we get the differences between the scenarios which show the effect of maintaining the expansion targets. So here are the results. The figures do not show growth rates like in the slides before, but those deviations between the scenarios. And on the left side, you can see the case of fast recovery, and on the right side, you see the results for the case of a slow recovery. And as you can quickly see, the deviations are very similar in both cases. So this means that the expansion of renewables has a similar positive effect on socioeconomic development, regardless of the speed of economic recovery. So renewable energies are a good option in both cases. The deviations increase over time because the positive effect grows with increasing expansion. So at the result in 2035, the GDP is 0.35% higher than in the scenarios in which the expansion targets are missed. And there are almost 40,000 more employed persons. So finally, a short look at our conclusions. The perspectives for sticking to an oil and gas-based economy have strongly worsened. Even before the COVID pandemic, a decline in demand for fossil fuels was foreseeable due to the fact that more and more energy importing countries are becoming more oriented towards a green economy and renewable forms of energy. And COVID further contributes that the market for fossil energies is no longer that attractive and that long-term price projections have been revised sharply downward. And our scenario analysis using the E3DZ model has shown that the expansion of renewables offers an opportunity to adjust Algeria's oil and gas-based economy. So maintaining the expansion targets for renewables results in a positive socioeconomic effect and can partly mitigate the negative effects of COVID. So now I want to thank you for your attention.
Thank you, Lisa. We have time for questions. Are there any questions? No, so I have one question. You calibrate some macroeconomic variable, assuming a drop caused by the COVID-19, but do you make robustness check to see how a change in your calibration on some macroeconomic variable can have an impact on your results?
I'm not sure if I understand your question. So a sensitivity check.
Yes, because you calibrate your model using 2020 data. And then you assume a slow recovery and rapid recovery. But how you can do you try to measure the impact of on when you calibrate your model? So excuse me, how you calibrate your model more generally? Which variable you use to calibrate your model and calculate your impact on GDP and employment?
Okay. Our model is, or in our model, empirical data is a very important component. So we have observed the developments last year, and the energy markets, which play an important role, have been adjusted by adjusting for volumes and prices. This was the main effect for the drop of the GDP, and the other variables have been adjusted to, for example, there were, I think, of the International Monetary Fund, there were specifications made for the development in Algeria. So we had adopted, for example, a drop of consumption of 15%. And then we have, yes, we have set it in the model.
Okay, but it's so it's your assumption, and if the drop you can see the impact on your result if the drop is higher or lower. Can you try the drop in consumption, for example?
What do you mean by?
You say that you assume a 50% of consumption drop. So can you see the impact on your result if you consider this impact if higher or lower?
Okay, no, we did not that analysis with sensitivity analysis. So okay. I can't say, sorry.
Okay. So it was my question. Okay, thank you for this for your answer. It was a very interesting presentation. Is there other question?
I had a quick question, if that's okay.
Yes.
I was just wondering about, hang on, what was I even going to say? Yeah, I was wondering whether you were planning to update the results, because you said that you were using summer 2020. Like, are you working on updating the results to take into account, you know, like more recent developments, or is there a reason why you've kind of stuck with the summer 2020?
Oh, I would like to work further on it, but unfortunately the project is over. Well, I looked it up how the real development was last year, and on the website of the International Monetary Fund, there was a publication of the GDP in Algeria last year. So in fact, it dropped by 6.0%, so close to our result, a little bit less negative. And the current projection for this year, for 2021, is a growth rate of 2.9%. So it is rather close to the slow recovery scenario, but the year is not over yet. So maybe economy can recover more rapid again.
Thanks.
We have time for other question? No, so we can listen our third presentation. Daan Hulshof, who will present a paper on title Renewable Electricity Subsidies and Windfall Profits, an empirical analysis of the Dutch support scheme.
Yeah, thank you. Can somebody help me out? How can I share my screen with you guys? I don't see the button. I've clicked everything in my.
It should be below with a green thing.
Oh yeah, now it's there.
Yes.
Maybe I missed it. Most obvious button in the screen.
No, maybe if someone else was presenting, you could not.
Okay, that could have been it. So probably you see my my presentation now. Great. Yeah. So since we were 3 in the session, I have a bit more slides than for 20 minutes. So I'll try to stick within 20 minutes like the other presenters. My name is Daan Hulshof. I am in Groningen, in the north of the Netherlands, maybe pretty close to Lisa. I'm presenting a project titled Renewable Electricity Subsidies and Windfall Profits, an empirical analysis of the Dutch scheme. And it's a project together with Michiel Mulder. He was my PhD supervisor. I've defended my thesis quite recently. Short outline, I will start by discussing a bit of background, pose a research question, say perhaps 1 sentence about related literature, show or illustrate a method that we applied to estimate the windfall profits, go over some of our data sources, present some results and conclude. So let's start with the background. This is a picture showing greenhouse gas emissions by source in the European Union. It's 2018 data from the European Environment Agency. And perhaps this does not come as a surprise to many of you, but electricity production, some heat production is in there as well, is the biggest contributor to emissions in the European Union, about 1/4 of total emissions. Transport is also a big one. This yellow chunk of 21.5% is basically an aggregation of all kinds of sectors. But electricity is a major source of emissions. Perhaps that's also then not a surprise that governments are targeting specifically this sector to reduce emissions. But actually, their targets are really ambitious. For instance, here in the Netherlands, we have a target of 70% of specifically renewable electricity in 2030. We come from 18% in 2019. Germany also has quite ambitious targets for 2030, 65% in 2030, but they were already a bit further in 2019 at 41%. Still, it's a challenge to attain these targets. Renewables remain generally more expensive still than fossil-based sources. So we really require policy intervention in order to meet these goals. We have options, trade schemes like the European ETS, taxes. We can subsidize renewables. We can set portfolio standards, for instance. And what we see in practice is that particularly subsidies have become highly popular. So out of the 135 countries with some kind of policy in place for renewable electricity, 111 have implemented policies, sometimes in addition to something else like a carbon tax or an ETS. And the subsidy expenditures are also already becoming quite serious. For example, in the European Union as a whole in 2017, total explicit subsidy expenditures amounted to a bit more than 78 billion. So it's already about 0.5% of GDP. So that's quite considerable already. Well, of course, there's benefits. We do this for something to attain these targets. In the European Union, this contributed to production of 1,003 terawatt-hours of renewable electricity. So if I just do this simple ratio of expenditure to terawatt-hours, that implies expenditures of 78 euros per megawatt-hour. This doesn't mean that this was the amount of support paid on average, because some of this production was also unsupported, of course. It's just to get an idea of orders of magnitude. Looking at the Netherlands, a bit more recent data, 2019, We are small. We only spent a bit more than 1 billion, so that's only 0.14% of GDP. So we also attained much less production, of course. 22 terawatt hours means implies expenditures of about 54 euros per megawatt hour. These two are also a bit difficult to compare because here in the Netherlands, in addition to this subsidy, producers can sell their electricity on the electricity market and generate some revenue there. Whereas in many countries, the subsidy is the only source of revenue, which may explain why this figure for the European Union as a whole is a bit higher. Just to get an idea about orders of magnitude. Because what I want to say with those figures is that these expenditures are already becoming quite serious, and we only need more because we need to attain these ambitious targets. So from that perspective, cost efficiency is quite critical. And thinking in terms of cost efficiency, what do we want from subsidies? Well, first, we want subsidies to trigger low-cost options. So we don't want to subsidize a solar PV panel that's in the shadow the whole day when there is one available in the sunlight, and that generates a lot more electricity, for instance. But we also do not want subsidies that are higher than necessary. So we do not want to give a project more subsidy than it needs. So we do not want windfall profits, right? Because then we can basically either reduce expenditure to achieve the same amount of renewable electricity, or we can achieve more renewable electricity with the same amount of expenditure. And the second point is basically what we investigate in this project. And it basically implies that for each project, right, if we want to eliminate all windfall profits, we promise a subsidy such that the net present value of an investor or of a project is precisely zero. But this is very difficult because projects differ from each other, right? Some projects have higher costs than others, and governments can also not observe perfectly what the differences in costs are, what the costs of a specific project are. So what do? Basically, they say, okay, we give all projects, for example, all onshore wind projects, the same subsidy, or we give all projects in a region that have some kind of similar characteristics, the same subsidy. And well, of course, what does that imply? If you give a whole bunch of projects the same subsidy, some projects will have more favorable characteristics and will earn some kind of windfall profits, right? That's kind of unavoidable with subsidies. And the question that we address in this project is basically, what is the extent of these windfall profits, right? So specifically, to what extent are subsidized renewable electricity investors, projects, I should probably say it's more accurate, earning windfall profits? Now, what have other papers done, and basically what is our contribution? Other papers mostly look at the efficiency of first best options, compare them, for example, to second best options. There's also a large literature that within this second best literature compares options with one another, mostly in terms of efficiency and effectiveness. But there's much less focus on these distributional effects, these distributional consequences. So that's really the contribution of this paper. So how do we estimate these windfall profits? Well, we focus on the Dutch scheme. Basically, we do an empirical analysis of the feed-in premium scheme, and we focus on onshore wind projects. We think it's interesting to analyze this scheme because it has been active since, well, a bit more than 15 years. And it kind of explicitly aims for this subsidy that achieves a net present value of zero for projects. And it does so by basically estimating an investment model where they assume the characteristics of a reference project. Also, within this time frame since 2003, several adaptations to the scheme were implemented that specifically aimed at reducing windfall profits. For instance, category differentiation, and well, basically the assumptions for the reference projects have been tightened over time. Just to show what these two changes mean, this is a map of the Netherlands, and before 2010, every onshore wind project, it doesn't matter what the location was or what its characteristics were, received the same subsidy. So we had this real uniform subsidy for all onshore wind projects. And after 2010, and basically it has changed a couple of times, but this was the situation in 2017, the scheme implemented category differentiation. So since then we have 4 categories. Here, each color represents a category, and a category is differentiated from another category by the average wind speed. So the red category represents a wind speed of more than 8 meters per second. The orange is wind speed of between 7.5 and 8 meters per second, and the bluest as the lowest wind speed. Makes some sense. So closer to the sea, so to the west coast, the wind blows harder, which means probably that you generate more electricity and that you, per unit of generated electricity, need a lower subsidy. So since then, projects in the blue area, for instance, receive a lower subsidy than projects in the green area, which receive, blue is of course the highest subsidy and red is the lowest subsidy. So 4 regions, 4 different subsidies, subsidy levels, I should say. Then tighter assumptions, just to show that that the characteristics, the assumptions for the reference project have also become tighter. Here are the assumptions for several characteristics of the reference projects for 2003, 2009, and 2018. And for 2018, there were 4 categories, and I've listed 2 categories here, the lowest and the highest wind speed category. But let's look, for example, at the assumed production level, which is denoted in terms of full load hours, which is basically just the amount of hours per year that the turbine generates its maximum output. So in 2003, the assumption was that these full load hours amount was 1,800, and in 2009 that was 2,200. So it's a tighter assumptions. I assume that you produce more. And in 2018, even in the lowest wind speed category, the assumed production was higher than the assumed production for, well, all projects in 2009 at 2,350 full load hours. Okay, so then our method. So how do we estimate these windfall profits? Point of departure, again, projects differ from one another. So probably we want to say something about how projects differ from one another. So what we would like to do, we would, instead of as the government subsidy does, so the government subsidy estimates the required subsidy of a reference project. And we would like to say something about how this required subsidy is distributed over projects within this category. And we want to compare this distribution with the actually granted subsidy. And ideally, you would have all this micro level information of every project and then estimate very precisely of each project the required subsidy. But yeah, the data to do that is not available. So what is our solution? Well, basically, we have 2 parts. First, in part 1, what we do is we take this investment model from the scheme so that the government also uses to calculate the required subsidy. But instead of assuming that all these characteristics are fixed, are deterministic, we estimate distributions for several key parameters, such as the full load hours, so the production, the wind conditions, and replace these deterministic assumptions by these distributions. And then we basically estimate the model with Monte Carlo simulations. So we just run the model a couple of thousand times. This results in an estimate of the required subsidy. And if you order these outcomes from low to high, you get a distribution. And we can compare this with the fixed subsidy. And we do this for all potential locations and heights. What does potential mean? Well, for example, we look at the wind conditions at all locations and all heights, or all relevant heights, I should say, in the Netherlands. So that means that we're not only looking at the installed turbines, but we also basically estimate the required subsidy on a certain location and height where currently there is no turbine. And we basically call this the potential, potential projects. And we do this for 2003, 2009, and 2018, 4 times, since we have 4 categories in the last year. And in the second part, we also estimate the required subsidy, but we don't use, but we do this now for actual projects. And here we only focus at the wind conditions and only at 2018, because specifically for this year, we actually know for all the projects that received the subsidy, what their full load hours were. So we kind of have this micro level data, but we don't have it for all the other variables. So why is it interesting to still do this? Because this allows us to compare the results with the potential projects. Because the potential projects are, of course, kind of the average of the potential projects is just a random draw. And if we compare this to the actual projects, we can say something about whether investors sort of take random projects or whether they are quite successful in taking out the projects with the highest windfall profits, which is what you expect from investors, right? They just go and start looking for the best projects. So this is our investment model. That's basically the government's investment model or the scheme's investment model. What do you want to do? You want to set net present value of revenues equal to the net present value of costs. Well, revenues, you have them over the lifetime of large T, capital T. Years are denoted by the small t. So we have production Q in year T, and we have the electricity price, and we have the subsidy. So PE, electricity price, subsidy S, multiplied by production Q is gross revenues. We pay some taxes tau, and we discount future revenues. On the cost side, we have the share of equity investment. So I should say here that we take the perspective of the equity investor. So these revenues and costs are really from the perspective of the equity investor. So we have the total, what are his costs? Well, we have total expenditure X. It's kind of the investment that you need to make for the turbine. Then the equity holders need to come up with the share E of that total investment. And of course, we have all kinds of operating and finance costs. So we have, again, some taxes to be paid. Pi here is an inflation parameter. So the costs over the years go up. And VC is variable cost, FC is fixed costs. Then we have some kind of tax advantage when we depreciate and we pay interest rates, D and I. And we have to pay some kind of annuity loan for the part of investment that is financed by a loan. What do? We equate these two to each other. Of course, there's S in there in the revenue part. We just rewrite the whole thing in terms of S, and then you get this kind of nasty expression. And then we say, okay, well, the scheme assumes some of these components like production are deterministic. Well, we think some of these are they follow some kind of distribution. They are stochastic. What are the inputs that we focus on? Well, we focus on the full load hours. So production is defined as full load hours times capacity. Capacity drops out of this whole expression, so we really focus only on full load hours. We focus on the lifetime of the turbine. We focus on the share of equity and on the required return on equity. And in the second part, we only look at full load hours. Probably because of time considerations, let's move on. So we get our data, for example, wind speed data. Here is a histogram of the, so we transform this wind speed data into full load hours. This is a histogram of the full load hours in 2009. And the red line is the assumption of the government. So what do? We take a whole bunch of theoretical distributions. We estimate the parameters, And we use things like archaic information criteria to basically fit the best distribution. In this case, it's a gamma distribution with scale parameter 131 and shape parameter 16.68. And we do this for all these variables and for all subsidy categories. This is again a histogram of the economic lifetime. The vertical red dotted line is the assumption of the government, assumes deterministically that all projects have a lifetime of 15 years. Well, we observe the lifetime of Dutch turbines, but we see that this distribution lies quite considerably to the right. So probably it's a bit of a conservative assumption. And for the equity share and required return on equity, we use data from a paper of Eckley and colleagues of 2018 for German turbines. They have a database with equity share and required return on equities over time. Now let's go to the results. So we do this Monte Carlo these are first the results for the potential projects. We run these Monte Carlo simulations. We generate all these estimates for the required subsidy. We order them from low to high. And what you get is this blue line. So on the horizontal axis, you have the required subsidy. And then if you order them from low to high on the vertical axis, we have the cumulative probability. And again, the vertical red dotted line represents the subsidy that was actually offered to projects. So this is the result for 2003. The subsidy that was offered to projects, to all projects, since all onshore wind projects receive the same subsidy, was 7.8 euro cents per kilowatt hour. And so what can we say from this result about the windfall profits? Well, what we do is first we simply look at what percentage of projects lies to the left of this vertical red dotted line. So how many projects have a lower required subsidy than the subsidy that was actually offered? In 2003, that was about a bit more than 80%. For instance. And we do a second thing to say something about the windfall profits, and that is to take any point on this blue line and subtract basically the value of the red line. That is, of course, the amount of subsidy that the project received too much, or that was basically the shortfall in subsidy, right? If it needed less, if it was located to the right of the vertical red line. And basically what we do is we calculate the average distance between these two lines. So that basically gives you an idea about the average amount of windfall profits. So the amount of subsidy that the average project received too much. So this is for the result for 2009, a bit less projects located to the left, 76%. You see the subsidy also went to the left, but the required subsidy also jumped quite far to the left, which is what you expect since the technology improved over time. Now to 2018, this is the lowest wind speed category. Again, the required subsidy went to the left. Also, the subsidy itself went to the left. And these are higher wind speed categories. So what do we expect? The blue line shifting to the left. Now here, a summary of the results. So in the first column with percentages is the share of subsidies that is located to the left, or the share of projects that is located to the left. And we see that in terms of this percentage, the scheme became less generous. So in 2003, 81% received too much, and that decreased in 2018 on average of all categories to 68%. What about the average windfall profits? Well, in 2003, the average project received 2.42 euro cents per kilowatt hour too much, theoretically, yeah, of course. And that's about 31% of the subsidy. Well, in 2009, that decreased a bit, and 2018, that decreased even further to about 0.9 euro cents per kilowatt hour. So in absolute terms, that's quite a big decrease, but in relative terms, it's still about 1/3 of the subsidy. And if you think about it, that's actually quite a lot. That means that for each euro of subsidy that we spend, we could have actually saved 32 cents and spent it on another project, for instance. So at least in theory, this implies that there's quite a lot of room to generate more projects with current expenditure in the Netherlands. Now, the results for the second part, looking at the actual projects. So this is again 4 of these pictures since there were 4 categories. Here I've added the new results, which is the black dot dashed or dash dotted line. And these are the results for the lowest wind speed category. So what do we see for actual projects? Well, for actual projects, we see that this distribution lies quite far to the left of the blue distribution. So suppose that investors would have picked random projects, then probably this distribution would have coincided with this blue line. But what do we see? We actually see that the required subsidy of actual projects is quite a bit lower. So they pick out quite favorable projects, which doesn't really come as a surprise, I would say. And we see the same happening in most of the other categories, except for this category. Here we see that a lot of the probability of the cumulative probability has exactly kind of the required subsidy as the subsidy that was offered. But this is mainly driven by 2 very large projects. And here in the third category, we again see kind of the similar result. Summarizing the results again in the table, what do we see? Well, the share of projects to the left of the actual subsidy is quite a bit higher than under part 1 with the potential projects at 85%, and average windfall profits were also considerably higher with about 1.3 euro cents per kilowatt hour, which equates to 50% of the subsidy. So that's really quite a lot, I would say. Concluding, what do we see? What do we find? What can we conclude? Windfall profits have decreased over time in terms of the number of profitable projects and also in terms of the amount of windfall profits per kilowatt hour. But in relative terms, windfall profits were actually quite similar in 2018 as to 2003 at 30%. So they have not been eliminated. And actual projects earn considerably higher windfall profits than the average project, than a randomly picked project. And this is probably because these investors have better information than the government and the guys designing the scheme about the characteristics of projects. Also, this category differentiation seems to have contributed to mitigating windfall profits. And that's it. Thanks.
Thank you for your presentation. Are there any questions? Yes. Gengyang, we listen to you.
Thank you for your presentation. This is very interesting. I would like to ask, have you controlled the growth rate of the sector when you do your analysis? The reason why I ask this question is because in another study I found that even if we provide how to say windfall subsidies as you defined, in the future, as a result, the investor will just invest more money because they see opportunities. So in the long term, if we estimate the data dynamically, perhaps windfall profit or excessive subsidies is not really a bad thing, because it will bail out more money from investors' pocket. That's my question. Thank you.
Thanks, Gengyang. I'm not certain whether I fully understand the point. So what I would be inclined to say is, so I would say, I need to say this. So if you increase the subsidy, of course, you are going to generate more projects. But, and let's take, for example, a look at the results here. Here we find, for example, in 2003, that the average sort of windfall profit was 30% in relative terms. So if we would have decreased the subsidy by 30%, yeah, of course, I don't know, can you see my mouse as well? Probably not, right?
Yes, yes, I can see your mouse.
Oh, you can see the mouse. Okay, so if we decrease the subsidy by 30%, that basically means that this line is going to move in that way. So let's say that it would have been somewhere here. Yeah, of course, all these projects located on this line would not have been profitable anymore. So they would not have been undertaken.
Yes.
However, suppose that you could tailor the subsidy to each project. That means that you would decrease subsidy expenditure. So if you would be able to give this project this subsidy, if you would be able to give this project this subsidy, you could still attain the same amount of projects by spending less subsidy, spending less on subsidies. And this is hard to do in practice because it's difficult to differentiate between these projects. But at least in theory, there is a lot of room to reduce subsidy expenditure and attaining the same amount of projects. It's difficult because you need to differentiate somehow between projects. So whether we can achieve this in practice is indeed a good question. And then to follow up basically on your first point about dynamic effects, yeah, in my view, if you reduce subsidy expenditures and attain the same amount of projects, I don't see any harm or benefit to the dynamic effects, right? The dynamic effects are probably the result of how many projects you realize and the learning effects that that those projects generate. So in that sense, I understand maybe your point that more windfall profits may not be a bad thing, but only, let's see, probably the ideal outcome would then be to receive the same amount of projects without generating windfall profits, right? Then we would not expect different dynamic results, I think.
Thank you for answer. My further question will be, have you checked because you have each year the average rate of the windfall profit, 30% or around 30%, and can you estimate the relation between this percentage with the growth rate of the renewable electricity sector? For example, for example, in 2003, the average is the windfall profit is 31%, and the next year, what's the growth rate of electricity, renewable electricity market? And then you can see if there is a how to say average dynamic effect or not, and you can conclude in average windfall profit is a bad thing for the growth of the sector or not.
Yeah, so
I think you got data on this, right?
Yeah, this would be, but maybe, yeah, so a sector approach would be basically kind of a macro view, right?
Yes.
It would kind of relate macro information with macro outcomes, but the project is much more, yeah, has a micro foundation. So what we don't really look at aggregate data, but we have an investment model for a project, and here we try, right? So I don't really see how I would integrate this macro data in my analysis. Also, yeah. So how does it play a role? So when production and installed capacity goes up, probably costs come down. So probably I should say something about how the improvement in the technology is reflected in this model. Is that something that would interest you?
And also the motivation of the investment, because you can perhaps a windfall profit will generate just a high growth rate of investment on this sector next year.
Yeah, I don't see that point, because when you offer a subsidy that makes the net present value, let's say at least 0 or bigger, then this project will be undertaken. You don't need to give windfall profits for a project to be undertaken. So if you give a subsidy such that the net present value is precisely 0, then you don't attain more projects compared to, or you don't attain more projects when you give windfall profits, right? You just need to give a subsidy such that the net present value is precisely 0. You don't need to give more, because a project will already be undertaken when you give the subsidy such that this net present value is equal to 0. You don't need to give more. So you don't generate more projects when you do that.
In my other study, I found that the subsidies for isolation is not the case, because first, the government have subsidized evidently more subsidies to the household, and then what happened is household will at once make some further project on indoor isolation. I will do the window, I will do the wall, because now there is opportunity. I will do this shortly.
Okay, but maybe we also need to consider that these are professional investors, right? These are guys that are investing for their own wallet. Maybe they're different perspective than households. And yeah, maybe I should stress again that I completely agree with your statement. When we are in a world where we offer a uniform subsidy, so when we have a uniform subsidy, then yeah, unambiguously, if we give a higher subsidy, we will generate more projects. But the idea here is, suppose that you can differentiate between projects, then a higher subsidy not necessarily leads to more projects. Actually, not at all. I think that's basically the key point.
Thank you for
Whether it's
in
practice is probably difficult. Thanks.
Lisa, you have a question?
Yes. So thank you for your very interesting presentation. I have a question concerning the calculation of the net present value of costs. Yes, right. I think you said the variable and fixed costs of the future for the wind energy plant are included. So I was wondering, where do you cut off? So I think you considered maintenance and operation costs, but do you also consider the whole lifetime of the plant? For example, the cost for the deconstruction, or where do you stop considering the costs?
Yeah, this is a good point. Decommissioning costs. Decommissioning costs are not included.
Okay.
So what we have is variable costs of operation that and fixed annual costs that are independent of your production. And yeah, kind of implicitly we have also the investment, which means that you would have to say something about the size of the turbine. But because everything on the right-hand side of the subsidy, so basically the fourth bullet point on this slide here, everything on the right-hand side is proportional to the capacity. So we don't explicitly have to say something about the size of the turbine and the investment costs per unit of per megawatt of installed capacity. That's kind of the upside. So what the only thing that's really explicitly included is variable costs per unit of production and fixed annual costs.
Okay, thank you.
Is there another question? No, so we're in time. It's great. So thank you, Gengyang, Daan, and Lisa for your presentation. It was very interesting. So I think if there is no question, we can stop the session here. So thanks again for your presentation.
Thank you, Anna, for moderating.
Thank you all.
Thank you.
Thank you.
Bye.
Bye.
Bye-bye.